Alright guys, we're going to give you just a brief tutorial on how to run a few calculations in Gaussian. So for this one I'm going to do the example of the eclipsed ethane and the staggered ethane. So to start with, we're going to do the staggered conformation first. So we'll construct our ethane first. So just brief review. This clipboard here is whatever molecule you'll produce in the Gauss view window. So whenever you click, it's going to produce a methane. Now if I want to produce ethane, just click on this hydrogen here. So what I have right there, if you look along that carbon-carbon bond, is the staggered conformation. You can see how none of those hydrogens overlap. And so this is pretty much ready to run a calculation. For last thing we're going to do is you're going to click on this here, which will clean it up just a little bit, which will make your calculation just run faster. So there we go. Now, to go ahead and run the calculation, we're going to come here to calculate, choose this first option, Gaussian calculation setup. And for this we want an optimization. We're coming to a minimum. And that's all we need in this window here. Next we're going to come to our method. So the one that we want to use isn't listed here, so we're just going to say custom. And then we can type in our method right here where it says additional keywords. So in this case our method is M062X. And then go ahead and hit update. So this box right here is where you're going to enter all of the extra keywords that you need to whenever you're running any of these calculations. Our basis set, which is pretty much the representation of orbitals that we're going to be using to calculate our energies. For this particular one, we're choosing 631G, and then we need a D right here. And then that's everything that we need in this particular window here. Last thing we need to do is come over to this tab that says General, and this is a default option that we don't want, so go ahead and just get rid of that. Once you've done that, your calculation is ready to submit to Gaussian, so go ahead, click Submit. You need to come up with a name, make sure you're paying attention to where you're saving this. So in this case, we're going to go call this ethane staggered, and looks like there's already a saved ethane staggered, so we're just going to override it just so we can see the calculation. And alright, so this was a relatively simple molecule, so it didn't take as long for Gaussian to run through, so we'll go ahead and say yes. And then you generate two files whenever you run a Gaussian job. You'll either get a checkpoint file and a log file. For the purpose of this assignment, we're just going to use the checkpoint file. And go ahead and open that up. And so here we have our optimized ethane. So all the bond lengths, all the bond angles, they've all been optimized to give this thing the lowest energy that Gaussian could find. If you want to see what that energy is, just right click in the window, come to results, and summary. And so we have this negative number right here. That's the electronic energy, which is close enough for our purposes for what we need for the total energy right here. As you can see, it's a pretty large negative number. So first off, this is in Hartrees. Normally you'll see energies in kilocalories per mole, so we'll convert that in just a little bit. And it's negative because this is the energy compared to a free nucleus and free electrons. So this is how much lower this molecule comes in energy once those bonds are formed. And then this information becomes even more useful when we have something to compare it with. So in this case, we're going to compare it to the eclipsed version of ethane. So we need a new window, and this time we're going to go ahead and make our eclipsed ethane. So start off with ethane. You can see that that's staggered. So now we're going to go ahead and change the dihedral angle. Just click right here on this button. That lets you do that. And then you select 4 atoms. The middle two, so atoms 2 and 3 that you select, those form the atoms. The bond between those two is the bond you're rotating around. So I'm just going to come here so you can watch that. And we want to go so it's totally eclipsed. So that's right at 0 degrees. So you can just enter in that angle right there. Hit 0 and OK. And now we should be ready to run our job. So this one, you don't want to hit the cleanup, because if I do, it's going to go straight back to the staggered conformation, because Gaussian knows that that is lower in energy. So now we can go ahead and come straight to calculate, calculation setup. And this time we want an optimization. And rather than going to a minimum, because I would just go back to our staggered conformation again, we're going to a transition state. Now, in order to make sure that it finds a transition state, we have to tell it to calculate force constants. So go ahead and say once there, and then our method is going to be exactly the same as what we did before. So custom, and then type it in right here next to the additional keywords box. So M062X, and then your basis set, it's the same as before. And then we just have to get rid of this option. And now this is ready to submit to Gaussian. So this one we'll call ethane eclipsed. And we'll say OK. Alright, now our job's finished. So once again, 2 files, checkpoint and a log file. We're going to use our checkpoint file. And here we go. So now we want to compare the energy of the eclipsed to the staggered. So right click, results, and summary. And so here you have one energy here, and you have one energy here, so we can actually calculate the difference. Going to go ahead and stick those in an Excel spreadsheet. The one that's closer to 0 or less negative is the higher in energy one, so in this case the eclipsed. As you can see, you got the 0.76 compared to 0.77. So we're going to highlight that, and then we're going to copy and paste that into an Excel spreadsheet. And then we'll come back and we'll grab the other one. So here's this one. Alright, and then we'll copy that. Stick that in our spreadsheet. And now we just want the difference between the two. So we'll take our higher energy one minus our lower energy one. And then there is our energy difference right there. And now, so this is in Hartree's. Last thing we need to do is convert to kilocalories per mole. So the conversion factor is 627.5095. And then we're just going to multiply that by that. And so our energy barrier, it looks like, is 2.79 kilocalories per mole. And then if you go ahead and you were to Google that and look up the rotation barrier for ethane, it should be something pretty similar. And that should be it.